Gauss law in magnetism. We have studied Gauss law in electrostatics. The Gauss law is applicable when, number one, the field is central, a force is central force. Second point, the force is inversely proportional to the square of the distance, means inverse square law. So in the electricity, in the electrostatics, we know that the electrical force is proportional to 1/d square. Similarly, in magnetism, magnetic force is also proportional to 1/d square. So we can apply Gauss law for magnetism similar to the Gauss law applied for electrostatics. There we have find the electrical field, and here we will find divided magnetic flux. So what will be the magnetic flux? If B is the magnetic field, ds is a small area, and so ds is a vector. So suppose this is the magnetic field B and this is ds area. Area vector will be perpendicular to its direction. Then the magnetic flux passing through it is d phi is equal to B dot ds. So if you want to find the total magnetic flux, then phi B will be equal to, we have to take the integral, surface integral round the surface, B dot ds. Now suppose this is the body which is in the magnetic field, and so these are the magnetic lines, field lines. So the number of magnetic field lines enters in this field will be same as magnetic fields which are coming out of exit. So net magnetic lines inside this body or this enclosure is 0. So the magnetic flux will be equal to 0. Therefore, the Gauss law can be written as, we put it here, Gauss law will be equal to surface integral B dot ds is equal to 0. So this is the Gauss law for the magnetism. In the electricity, we have surface integral of E dot ds is equal to summation of q bata epsilon 0. Now we will study the magnetization of the material. Magnetization of material means if we place the material in some magnetic field, what will happen and how it will be magnetized. So we know that all the materials are made up of atoms, and in atoms there is a nucleus and electron is revolving around it. So what will be the magnetic moment? Magnetic moment of this electron will be equal to capital M is equal to the current multiplied by the area of this circle. So the current will be equal to EV bata 2 pi R. Current is equal to charge divided by time. Here time is time period. So 2 pi R bata V. So it will be, pi will cancel, 1 R will cancel. So it will be equal to EVR bata 2. Now what will be the direction of magnetic field? The direction of magnetic field is given by the right hand thumb rule. So if this is the direction of, suppose, current. The electron is moving in this direction and current is in this direction. So the magnetic moment will be outward. So here in this case it will be perpendicular and outward. So in atom there are not a single electron, there are many electrons are there. They are orbiting in the different orbits, And we know that in first orbit there are 2 electrons, in second orbit there are 6 electrons, and so on. So there is a pair. When we have a pair of the electron, then the one electron is moving this side and another electron will moving in the opposite direction with the same radius. So for one pair, magnetic field will be generated and magnetic moment will be opposite to one another. Here it was this side, and when it is like it downward, so they are M1 and 2 are equal. So net magnetic field will be equal to 0. So for the pair of electron, net magnetic moment capital M will be equal to 0 because one magnetic field is upward. Then for the second electron, it is downward, so net will be equal to 0. We take the example of helium. Helium 2, helium 4 means there are 2 electrons. So 2 electrons means the magnetic moment will be equal to 0. So molecules which are like helium means for the element in which there is a even number of electrons, then the magnetic moment will be equal to 0. So M will be 0 for the atoms having even number of electrons or even number of Z is the same, even is same. And if it is not even, then there will be a magnetic moment of each atom. There are not a single atom. The direction of each magnetic moment will be different. So the magnetic moment will be for the one atom, second atom, third atom. So they are randomly distributed. So the total magnetic field of this sample, not of the atom, of this sample will be equal to 0 because of the randomness. Now for paramagnetic substances and ferromagnetic substances, we are having 3 types of substances. One is the diamagnetic substance, another is paramagnetic substance, and third is ferromagnetic. So for paramagnetic substance and for paramagnetic substance, if we apply the external magnetic field, here there was no external magnetic field, here we apply the external magnetic field, then due to magnetic, the electron, the atoms or the magnetic moment of atom will try to align in the direction of magnetic field, so the magnetic moment will increase. Now in the case of ferromagnetic substance we explain by the theory of domain. What are the domains? Domains are very small volume in which the direction of magnetic moment is same. So when there is no electrical field, no magnetic field is applied, the domains are random. But when we apply the magnetic field, then the domains will try to be in the direction of the magnetic field. So magnetic moment will increase. So for paramagnetic substance, due to the magnetic dipole, and for magnetic substance, ferromagnetic substance, due to the domains, there is the alignment and the magnetic moment will increase for both as we apply the external magnetic field. Now for the third type of diamagnetic substance, M is equal to 0. Just we have taken the example of helium. M is equal to 0. There is a pairing of electrons. So net magnetic moment of each atom is equal to 0. So when we apply the external magnetic field, what will happen? There will be induced dipoles are produced. Due to the magnetic field, induced dipole are produced, and the direction of induced dipole by the Lenz's law, which we will study in next chapter, by the Lenz's law, they will try to oppose it. So magnetic moment which was equal to 0, but now due to the external magnetism it will opposite direction. So such materials are repelled instead of attraction. So when we apply the magnetic field, then these diamagnetic substances, they are repelled by the magnetic field, whereas the paramagnetic and ferromagnetic, they are attracted towards the magnetic field. Now how to find that which material is paramagnetic, which is diamagnetic, which is ferromagnetic? We can have a experiment like this. We are having a solenoid. The large number of turns are there, solenoid, and current is passing through it. So when the current passes through the solenoid, as we have learned earlier, there will be a magnetic field, and magnetic field will be maximum at the center. Now we will suspend a substance for which we have to find the nature of the magnetic, whether it is a paramagnetic, ferromagnetic or diamagnetic. We put it here, and this is a spring, so it is a sensitive balance. So when we put it and we on the current, then if it is upward, means it is repelled, then it will be diatomic. So what the diatomic substances? These substances are mercury, silver, bismuth, copper, carbon dioxide. Now these substances will be repelled, so it will move upward. So it will be repelled by this magnetic field produced in this solenoid. Now for a paramagnetic substance, the example of paramagnetic substance is chromium, tungsten, aluminum, magnesium, etc. Now then they will be attracted. So it will be, the pointer will go down. So means it will be attracted by the magnetic field. So it will go from here, it will go from diatomic, will go from higher magnetic field to lower. The paramagnetic substance will go from lower to higher magnetic field. So it will be, the pointer will come downward for the diatomism. And for ferromagnetism, even if we reduce the current is less, magnetic field is less, even then there is a attraction very high. So the example for ferromagnetic substance is iron, nickel and cobalt. So if we have a diatomic molecule, if we have a diamagnetic molecule, then there is a repulsion. So this sample will go from higher magnetic field to lower, it will go, the pointer will go upward side. For the paramagnetic substance, it will go from weaker magnetic field to lower, so it will go downward. For paramagnetic substance, it will go still more downward. So the force of attraction, the force will be more. So we can say that paramagnetic substance will go from weaker to stronger magnetic field. Ferromagnetic substance will also go from weaker to stronger field, whereas diamagnetic substance go from strong to weaker field. So they will be repelled, and for these two cases there will be a attraction. Now we will study the few definitions which are important for the magnetic material. The first definition is intensity of magnetization, and it is a vector quantity and written as I vector. This is the vector quantity. Now when we put the magnetic substance in the magnetic field, external magnetic, what will happen? The magnetization or magnetic moment will increase. So the net magnetic moment per unit volume is known as the intensity of magnetization. So when we put the substance in the magnetic field, then due to the external magnetic field, its dipoles or diamonds are aligned and the magnetism will increase or it will be magnetized, so magnetic moment will increase. So the net magnetic moment per unit volume means we divide by the volume, then it will be a intensity of magnetism and its unit is ampere per meter and it is a vector quantity. Now second is magnetizing field, capital H. This is also a vector quantity. So magnetizing field means you have a, suppose we apply the magnetic field on the substance, then what will happen? Due to the external magnetic field, there will be, the material will be magnetized. It will have two types of magnetism. One magnetism is due to the external field and second magnetism is due to the magnetization of the substance. So total magnetism will be equal to the actual magnetic field, that will be equal to the sum of two, which is external plus internal. This will be equal to the sum of applied magnetic field plus magnetic field due to magnetization of the material. So B will be equal to B0 plus B magnetic. So B, we can write B is equal to, B is proportional to the magnetization, total magnetization or total magnetic field will be depending on capital H, which is the magnetizing force. So when capital H is more, I is more. So the total magnetism or total magnetic field will be proportional to sum of H and I. This will be due to the external, this will be due to the internal. So we can write V is equal to mu times H plus I. Mu 0 is constant. Mu 0 is the permeability of the vacuum. So here we divide it here and we will find that H will be equal to B bata mu 0 minus I. So this is the magnetizing field and its unit is also ampere per meter. This is a vector quantity. So B magnetization, here B magnetization will be equal to mu 0 into I. Here two factors. This is equal to mu 0 H plus mu 0 I. So this is external B0 and this is due to the magnetization Bm. So B magnetization will be equal to mu 0 into I. So now if we do not have any material, means there is no material inside it, means there is a air or there is a vacuum, then what will happen? When there is no material, then I will be equal to 0. It is not magnetized. When it is not magnetized, I is equal to 0, then B will be equal to, the magnetic field B will be equal to mu 0 into H. Or we can write B0 is equal to mu 0 into A. Now this 0 suffix, this have a suffix or why it is given? It is given that when there is no field, there is no medium or there is a vacuum, then the magnetic field will be equal to B0. It indicates that there is no magnetic material or there is a vacuum or air. Next definition is magnetic susceptibility, and it is as chi m, m for magnetic, because chi electrical भी होता है, chi magnetic होता है. This is chi m means magnetic susceptibility. So we know that as we increase the H, I will increase. H is more, I will be, so I will be proportional to H. Means the intensity of magnetization is proportional to magnetizing field. So I is equal to chi m into h. This is the constant. So chi m will be equal to I bata h. So the unit of I is ampere per meter, h is ampere per meter. So chi m ki there will be no unit. It is a unitless quantity. Now the magnetic susceptibility for we can have for the diatomic substance, for ferromagnetic substance, and for the paramagnetic. For diamagnetic substance. Now in diatomic there is a repulsion. So the magnetic susceptibility will be less than 1 or it is negative. Or it is negative. For paramagnetic substance, it is greater than 1 because I will be greater than H. So, and in the case of ferromagnetic substance, this is very, very greater than 1. So, we can say that the magnetic susceptibility is negative for magnetic substance, it is positive and greater than 1 for paramagnetic substance, and it is very, very greater than 1 for ferromagnetic substance. Permeability. So permeability is for the magnetic field and magnetic material. Similarly, in the electrostatics we have permittivity. Permittivity is opposite to the permeability. Permittivity will increase the magnetic field, whereas permittivity that decreases the electrical force. So what is the permeability? It is the ratio of magnetic field inside the magnetic substance divided by magnetization field. So when we apply the magnetizing field H, then the magnetic field is developed in the substance, then the permeability is ratio of magnetic field inside the material divided by the magnetizing field. The unit is Newton per ampere cube, or it is Henry into Henry per meter. So either you can write Newton per ampere cube or Henry per meter. This is the unit of permeability. Now what is the relative permeability? Relative permeability of the material is mu r. Mu r is the relative permeability of the material. That will be equal to the ratio. Relative permeability is ratio of permeability of the material divided by the permeability of the vacuum. So the relative permeability, it is the ratio of permeability of the medium and the permeability of the vacuum. That's a mu r. It is a dimensionless quantity, no unit, because both are of the same unit, so they will cancel. So mu r is dimensionless quantity. Now we have to find the relation between mu, chi, b, h, and so on. So if we apply the magnetic field on a substance, then what happens? As I told earlier, when we apply the magnetic field on the substance, there are two types of magnetic field. One is magnetic field due to the external magnetic force plus the magnetism that is developed in the material. So total magnetic field B will be equal to B0 plus B magnetic, as I told earlier. Now what will be equal to B magnetic? B magnetic will be equal to mu0 into I have told earlier. B0 is equal to mu0 into H. When we substitute it here, and we know that chi is equal to I beta H, we have defined it, or chi m into H is equal to I. So we substitute it. So B is equal to mu0 mu 0 I plus mu 0 H. This is mu 0 H and mu 0 I. We take H common, so B is equal to mu 0 H plus chi m into H कॉमन आ जाएगा. So B बटा म्यू, B बटा H को डिवाइड कर दे. B बटा H will be equal to mu 0 into 1 plus chi m मैग्नेटिक. So B बटा H क्या हो जाएगा? म्यू. Permeability of the medium will be equal to permeability of the vacuum or air 1 plus chi, or mu divided by mu 0 is mu r. Mu r is equal to mu divided by mu 0 will be equal to 1 plus chi. So here we say that the mu r, this relation is very important. Mu r is equal to 1 plus chi. For diamagnetic substance, we know that chi is negative. So the mu r will be less than 1. For paramagnetic substance, chi is positive, so it will be more than 1. Mu r will be more than 1. And for validity, mu r is very, very greater than 1.